Hello, my name is Kanjana Silak from Suranadu University of Technology. Today I will present my research about molecular simulation for structural comparison of amorphous polyethylene imine and polyethylene oxide. In this work, I was interested in studying polymer electrolyte property using polyethylene imine (PI) and polyethylene oxide (PO) in comparison. Here is the first step of our work. The objective of this is to develop the simple IS model for PO and PI based upon both molecular mechanics and ab initio electronic structure calculation, and validate this IS model by comparing the conformational dependent property with experiment, and to generate an equivalent Vao-amorphous structure of PO and PI for prediction time molecular and material property in comparison with experiments. Polymer electrolytes are thought to solve in high molecular weight polymer with its ionic mobility. In this work, PO and PI are used as polymer electrolytes, and we want to compare the molecular and material property of PO versus PI, which has very similar structure but have quite different ionic conductivity when mixed with salt. The first step of our multiscale simulation starts from the rotational isomeric state or RIS model. For these two polymers using both quantum chemistry and molecular mechanics calculation. For the first approach, we start from the refinement of the original IS model for PO and PI from ab initio quantum chemistry by neglecting the third-order interaction, and then reduce the original 9x9 statistical weight to 3x3 dimension. The second approach is to construct the numeric 3x3 statistical weight matrix directly from the conformational energy map from molecular mechanics calculation of representative segment of polymer. After we got the IF from those two methods, we then calculate the conformation-dependent properties, including the characteristic ratio, dipole moment ratio, and their temperature coefficient. For PO, the characteristic ratio, we found that the IS model from ab initio gives better agreement to experiment than molecular mechanics method. Both IS models give characteristic ratio larger than experimental volume, especially from OPLS, but smaller dipole moment ratio. For PI, both IS models give the characteristic ratio larger than experiment. As we will develop the Coscan polymer model in next step, and the difference is not too much, we will use this new IS. After we get the IS model from PO and PI to simulate the bulk stem with multiple polymer chains, we need to introduce non-bond interaction. In our case, we will employ the Raynaud zone potential between the cos-gain bit. One bit is equivalent to 2 backbone atoms. Then the cos-gain polymer chain will map onto the second inlet diamond or through an ND like this. Last, amorphous PO and PI both generate an equivalent using Multiscale algorithm in discrete space. After that, the fully atomic amorphous PO and PI model can be obtained by the reverse mapping produced to recover the missing atom followed by energy minimization. From the fully atomic model, we then calculate Hilbert solubility parameter. The experimental solubility parameter of PO is equal to our calculated volume. In addition, we predict that the solubility parameter of PI may be smaller than PO, which may be lead to different intermolecular interaction, as PI can have hydrogen bonding. To validate the atomistic model, we then calculate the Newton scattering structure factor. The prediction and experimental in the position and shape of scattering curve are in the closed segment. This is my conclusion. Thank you for your attention.